The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or to view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
So welcome to our special class with half the people gone for Thanksgiving. You guys are the chosen few, so I'm pleased you're here. So I'm just going to say a little bit about models versus data, and then I'm going to go back to boundary value problems, and talk a little bit about how you handle really big ones. Yeah? Yeah. Yes. And in fact, these are even going to be on the video, because the guy just fixed the video, so it'll be recorded. All right. Yeah, I'm sorry. He said the video was broken last time, so the recording didn't work. All right. So when we're talking about models versus data, a really critical question is whether the model is really consistent with the data or not. And how do we know this is really true? So we talked about how we can figure out some sort of chi-squared maximum that we would tolerate. So maximum that we tolerate, we call it Q, capital Q in the lecture before. And so we think if we can find a chi-squared of theta that's less than this, then it's at least plausible that our model's true, right? Or alternatively, if all chi-squared of thetas for any value of thetas are greater than chi-squared max, then we would say the model is false or something else is really wrong with our experiment, right? That's what we say when we're saying we have a maximum chi-squared that we would tolerate. So a critical question with this is whether we really found the very best fit value of the parameters. In some simple problems, you might have linear dependence on the parameters, and then there's only one best fit, usually, as long as you have a non-singular set of equations, and everything will be fine, there's no trouble. However, more commonly, you have equations which are singular or close to singular, and also you normally have nonlinear dependence between the model predictions and the parameters. So for example, I do kinetics. We always care about the rate coefficients, the k's, and they always come inside a differential equation, right? You always have like d concentrations dt is equal to some terms, and some of them are, k concentration I times concentration j, whatever one it is, ij. Right? You have a lot of terms like this, bimolecular reaction terms, and these k's, some of them I don't know, and so these would be one of my thetas. So this would be, theta 17 would be one of these k's that I want to determine. And when I have a differential equation like this, when I integrate it, the k is always going to come in non-linearly in the solution, right? So when I integrate this solution, even in the simplest case, you get things like c of t is equal to a e to the negative kt. That might be a really super simple case if you have a linear kinetics. The k is still coming in non-linearly to the predictions, right? And if you have anything complicated, you can't even write it down a closed form expression, and you have to integrate with OD45 or OD15s. And so the relationship between k and the concentrations that you measure can be really complicated. So it's always nonlinear in my world. All the models are nonlinear. And I think there's many other situations like this. So if you do try to measure a diffusivity, it might be possible to set an experiment where you'd expect a linear dependence between something you measure and the diffusivity, but most likely not. So most likely it would come in non-linearly somehow, and you'd have some model for it, and you'd have a nonlinear dependence between that number and the numbers you would measure, right? And almost all the properties are like that. So because you have a nonlinear dependence, then you have to worry about how many minima do you have in your surface. So chi-squared of theta is a nonlinear function of a lot of variables. And typically, it won't just have one minimum. It'll have a whole lot of local minima. Now, one of those is the global minimum, and that's the one you sort of want. That's the very best possible fit. But you normally won't know how many minima it has. And so no matter how many minima you find, you don't know if you're done. And you don't know if you really found the best fit. Okay? So just because all the ones you found so far are bigger than chi-squared max, you might not be ready to write that article to Nature to claim that the laws of physics are incorrect because you're not sure you really found the very best fit. Okay, so that's one of the many problems of trying to figure out if a model and the data are really consistent. Now, that particular one you can overcome if you can find a guaranteed way to find the global optimum, to find the very best possible fit there is. And some people spend their life working on this, and one of those people is Professor Barton in this department. And so he teaches a class how to do this, and there are actually methods to do it. So if you want to see the application of this to kinetic models, there's a paper by me and Professor Barton, and the lead author is one of his former students, Adam Singer, in JPhys Chem, and it just shows how you can use global optimization to guarantee you have the very best possible values of parameters. And then they'll show you what happens. So this is a case where the experimental data was measured by one of my students, James Taylor, and that's the things with the error bars. And he did a lot of hard work to make sure he had pretty good error bars, and he really knew what they were. And so he had those points. So he measured a lot of points. This measuring of a lot of points is a key thing. So that means his degrees of freedom is very large, because he's many, many different time points along the way there, and he has error bars in all of them. And so because the degrees of freedom are very large, it actually makes it a very good constraint on the model. It tests it very thoroughly, where if you only measured 1 point, then that's not a very good constraint. Now, what James had done, and we published a paper in 2004 where he did it, where he said, you know, when I do my fits, this is what I get. I get these kind of purple and green things, and therefore, they're all outside the error bars, and therefore, I publish in the Journal of Physical Chemistry, I claim this model is wrong based on my experimental data. Okay, so we published that in 2004. It was accepted by the referees. It's in the literature. You can read it. Don't believe it, though, because Adam Singer went back and did global optimization using the same model, and his red line goes right through all the points really well. Do you see that? You can see the red line there. See this red curve? That's the true best fit. And so all the fits that James had found were all local minima in the chi-squared surface. And when he actually found the best fit with Adam's fancy method, then it turns out that actually the model matches the data like perfectly. So that's definitely true. So what we could publish the first time was completely wrong, because we said the model disproved the data, but in fact, the model proved the data. I mean, the data proved the model, or was completely consistent with the model in every way, in great detail. So I was a little embarrassed. So then James also, in the same paper, had found, and they could measure another condition, a slightly different case, and actually was looking at a different solvent. And in this case, he found this green curve as his best fit, and it looked pretty good by eye, though you can see it's sort of skittering on the tops of the error bar bands. And so this is one where he said, you know, if we do the statistical test, there's like a 5% chance that you would measure data like he measured if the green model was the truth. And so we said some wishy-washy words in the paper, basically because we weren't really sure if it was consistent or not consistent with the data. But in that case, Adam used his fancy global optimization techniques and found that James's fit was actually not that far from the global optimum. And he got the red curve there marked by the red arrow. And that one, it looks pretty good. It actually sort of goes through the data. But it doesn't really do it right. And found that, you know, it's the confidence interval is only 16%. So it's only a 16% chance, one chance out of 6, that James would have measured the data he measured if that model was true. And now we're sure that we have the global best fit. So now we're like thinking, well, you know, maybe we should say that the model is not true for this case, because it's an 84% chance it's not true anyway. So actually, we got it wrong both ways. So in the first case, we said that our data disproved the model. And in the second case, we said that our model was pretty good with the data, but actually they were both wrong. So the one was wrong, that actually the data did prove the model was correct for the first case, and it actually looks a little fishy for this second case. So anyway, this is just a concrete example to make you be a little bit more worried about what you do when you do these fitting things. Now, there's a variety of ways to try to do the least squares fitting to try to find optima. There was a guy named Carr from University of Minnesota, and he published a stochastic way to just try a whole lot of different initial guesses. And that usually works to find the global minimum. But if you really want to have a guaranteed global minimum that you're absolutely sure definitely is the global minimum, then you really need to use the global optimization methods, and you really should talk to Professor Barton. And for these kinetic models, he actually has a distributed code called GDoc that will just find the global optimization as long as you don't have too many kinetic parameters. I think if you go up to about around six adjustable parameters, it can handle. If you have more than that, then usually typically not. But because the problem with the global optimization methods is they scale exponentially with the number of adjustable parameters, or number of things you're trying to optimize. Now, on the other hand, if you have a model that you need to use more than 6 adjustable parameters to fit your data, then you might want to try to think of a different experiment, because you know the famous saying is like, give me n parameters, I can fit an elephant. So if you have more than 6 parameters and you're trying to fit some data set, probably if you do it right, you'll find a fit, but it may not really prove anything. So from that point of view, Professor Barton's code, GDoc, is pretty convenient for doing this nonlinear optimization. So that's a code for nonlinear optimization with differential equations embedded. And they can be stiff, and they can be large. It doesn't matter. What really matters is just the number of adjustable parameters. That's the cost. All right. Now, there was a really good question that you asked, I think, in class last time, maybe the time before. And it was, what happens, so let's get different cases you get. So one case you get, if chi-squared theta best, your best fit parameters, is a lot bigger than chi-squared max, then you're ready to say the model disproves the data. Right, so that one you're okay. If chi-squared of your best fit is less than, or significantly less than chi-squared max, it has to be less, much less, but really less, not equal, then you're really happy to say that the model's consistent. The model and data are consistent with each other. And in this case, what you would normally do next is determine the confidence intervals on the thetas that you adjusted, right? And if you read the chapter in numerical recipes, for example, or some of the notes online, it can tell you how to do this, right? And so that was okay? It was okay. So the case that's really problematic is you find chi-squared theta best, and it's less than chi-squared max, so you think the model is consistent with the data, but it's pretty darn close to theta squared max. And so then you have to figure out, well, the weird aspect of this is I now have, here's my famous plot of theta 1 and theta 2. So I have 2 parameters I'm adjusting. Theta 1 and theta 2, here's my best fit. If chi-squared max, if the curve of constant chi-squared max is something like this, this is chi-squared of theta equals chi-squared max. If it's like that, then I have some big region of a lot of different theta values that give it pretty good fits. And I'm happy to draw confidence intervals, like draw lines here and here, for example, and say that's the confidence interval in theta 1. And I'm all right, okay? And I might, it's sloped here, so I might want to tell people about the covariance between theta 1 and theta 2. All right, but I know what to do. It's fine. Now suppose this is the case that's like this, where chi-squared theta best is significantly less than chi-squared max. Now suppose instead chi-squared best was very close to chi-squared max. So then here's chi-squared max. This is chi-squared of theta equals chi-squared max. This is the good case. Here's the bad case. So in the bad case, there is some region of thetas that the model is consistent with the data, but it's very tiny. There's a little tiny range of theta values that would make the models consistent with the data. Now what's weird about this is that my best fit is not very good. The chi-squared is almost up to my chi-squared, the maximum chi-squared I would tolerate. So that means my deviations between my model and data are pretty bad, like this plot actually. Okay? And so I'm like, it's possible. I was a little bit unlucky and my data set is pretty far off, but still within the possible range. And so maybe the model data are consistent. But then when I try to compute the confidence intervals on my parameters, there's only a really small range of parameters that are going to give good fits here. Because the best possible fit is this red line. There's no choice of the parameters that's going to go through all the circles, right, with this model. So now I'm like, well, what's going on here? So if I went ahead and did it the same way I did before, I draw my confidence intervals like this and say, okay, wow, I've done an amazingly great job of determining theta 1. I know theta 1 very, very, very precisely. And the same for theta 2. Here's theta 2. It's got to be in that range. Man, I've really done a great job. So, I'm awesome. But I'm only awesome because my original best fit wasn't very good. So this is might make you feel a little sick in your stomach if you're getting ready to publish in Nature, right? And then if the reviewers are on their game, you might get something really scathing back from the reviewers. So there's kind of two ways to play it at this point. One way is you are absolutely sure that your equations are correct. You are Sir Isaac Newton. You have just written the law of gravitation. You are measuring the orbits of the moons of Jupiter, and you are sure that your equations are right. And so, my problem is my antiquated my telescopes of 1600 are not that great, and so I think I have maybe I misestimated my error bars on my measurements. Maybe I have some aberration or something. The angles are off, right? When I twist the telescope, it looks as if the star moves or something, right? Okay, so that's one possible way to go, is say, I really believe the model, and so I believe this is the truth, and I really believe my chi-squared max should be what it is, and I double-checked my error bars, and I think it's true, so I think I've done a great job, and I should publish it in Nature, because I've determined these parameters with 17 more decimal places than anybody ever could before. Okay? So that's one way to look at it. The other way to look at it is what's recommended in the Numerical Recipes book, and they say, don't use, instead of writing the equation to be chi-squared of theta has to be less than chi-squared max, they say when you're computing the confidence intervals, instead write chi-squared of theta has to be less than chi-squared best fit plus chi-squared max. So they say, don't use a stinky little circle here, draw a nice big one around there. And what is this saying? I guess it's saying is I don't believe that my poor agreement between the model and data justifies me declaring very narrow parameter values. So I just use the kinds of parameter value confidence intervals that it would have actually computed a priori when I was doing my experimental design. I think that's really how well I can determine stuff. And I think there's something that's wrong that my chi-squared best fit is so bad. Maybe I didn't do my global optimization right, and so I have the wrong parameters. Maybe I estimated my error bars, and so my chi-squares are all off. Maybe, I don't know what else happened. Something happened, and I don't believe I'm that good. So therefore, I'm going to quote much broader confidence intervals, which means much less precision in my determination of parameters. And that's what the numerical recipes guys recommend you should do. But it's up to you. And I've seen it both ways. So in the people who won the Nobel Prize for the dark energy, do you guys know about this? So if you ever saw the data there. So that's one where they said, they were using Einstein's theory of relativity, general relativity. They say, we believe Einstein. We believe that equation is true. And we're not going to, the fact that the data only matches when you choose a certain value of the cosmological constant, we're just going to go with it. And we're reporting that's the value of the cosmological constant. Now, some other people might say, that's kind of goofy theory. Einstein changed his mind 6 times about whether he put the cosmological constant into the equation at all. So I'm not so confident, and I would report something different. But they went with their gut. They said, we believe Einstein. They went with it. The Nobel Committee agreed, and they got the Nobel Prize. So, you're taking your chances. The numerical recipe guys are more like engineers. They say, we don't believe models that much anyway. Let's just use more conservative confidence intervals. Any questions about this? Okay. All right. So now I'm going to change topics. And we'll change to operator splitting. So if you remember, back when we were talking about boundary value problems, we're often trying to solve problems that are like this. All right, so this is the conservation equation for a species in a reacting flow situation. So you have some convection, you have some diffusion, you have some reactions. Now in my life, I have a lot of models. I have about 200 species in them. So this K is 200 different variables. And then you have these equations, and on top of them you have the Navier-Stokes equations for the momentum, conservation, and continuity. And so this is actually a pretty bad set of equations. And typically the chemistry is stiff because I have chemistry timescales that will be like in picoseconds, sub-nanosecond timescales. And I'm caring about simulating, in my case, maybe I've advanced new engine burning some fuel. And so we're running over a simulation of a piston cycle, maybe 10 milliseconds. But the chemistry is sub-nanosecond. So then you multiply it out. So that's like I'm going like 10 to the minus 2 seconds down to 10 to the minus 10 seconds. So that's 8 orders of magnitude difference in time scales. So I'm in a bad way trying to solve this equation. And I have 200 of these guys coupled to each other. And then I have to think of what my mesh looks like. And I'm trying to simulate inside a piston. Actually, I have a moving mesh because the piston's compressing. So the equations are kind of complicated for even what the mesh is doing. And then I need a bunch of mesh points there because do you guys know the Kolmogorov scale? Have you guys learned this yet? No, it's a scale of like the minimum eddy size if you have a turbulent flow. And that's pretty darn small also. So it might be submicron. And so I have length scale, natural length scale that's like microns maybe. So 10 to the minus 6 meters, but the piston diameter is a couple centimeters. So again, I have like 4 orders of magnitude between the mesh size I need to resolve the physics and the size of the thing. So I need about 10,000 points across the cylinder, but it's a 3D problem, so I need 10 to the 4th times 10 to the 4th times 10 to the 4th, so I need 10 to the 12th mesh points. And then I have 200 variables, state variables at each mesh point. So I have 10 to the 14th state variables. So how much memory do you have in your computer? How much RAM? You have probably like 16 gigabytes. So you have 10 to the 9th bytes, is that right? No, what's giga? 9th. Okay, so 10 to the 10th, sorry. 10 to the 10th bytes, but I have 10 to the 14th state variables. So I have a problem. So then you have to figure out how you solve it. So there's 2 schools of thought of how to solve these equations. The school of thought which has actually been the most successful so far, but is not readily available, is to get the government to build you the biggest possible computer in the world with as much memory as possible. And then you can actually keep track of your state vector, all 10 to the 14th elements. And you reserve this whole computer for yourself for a month, and just run it, and you figure out how to parallelize all the calculations, and you just use an explicit solver. And so that way it's just straightforward. All you're doing is you're computing, y of t plus delta t is equal to something, and it's just an explicit formula, ODE 45, fancy version of that. Okay? And it's just algebra, and you just add them up, and no problem. But this is a limited feasibility thing. This only became possible about 3 years ago when they built a computer that actually had enough memory to store the state vector. It's also, if the equations are too stiff, it still doesn't work because the step size, the time step you need to use is so small. So say it's 100 picoseconds. You're trying to get it out to a millisecond, so you need 10 to the 8th something time steps, which means you need to use double precision numbers all the way through. But if the government builds you a 64-bit or 128-bit machine, then maybe you can do it. But anyway, this is like a very special kind of approach. So now most people, including me, don't have access to that kind of computer power. Actually, if you want to read about that, so the woman who does that is Jacqueline Chen. And you might want to look on the internet and see about her. And somehow she became buddies with the people in charge of the supercomputers. And so they're happy to give her a month of the best computer in the world every year. And she runs some awesome, really awesome calculation that's exactly right, solves everything, has all the state variables 10 to the 14th. It's fantastic. And that's like currently that's the benchmark for how people test approximate methods for how to solving this, because she actually has the full solution numerically out. Converged. But this, again, it's like a limited applicability. So a lot of people are working on approximation methods to try to solve this equation if I don't have access to such awesome computer resources. And the general idea of them, well, there's two ideas. So one idea is somehow get rid of the turbulence. Okay, and so what they do is they use a mesh that's coarser than what you would need to resolve the Kolmogorov scale. And then they use models for what happens for itty-bitty tiny eddies. And those are called subgrid scale models. And this whole approach is called large eddy simulation. And the idea is you keep track of the large eddies, the big recircularization zones. That's modeled explicitly. But you don't keep track of all the itty-bitty tiny swirling off little eddies that last for a little bit of period of time before they dissipate because of diffusion. Okay, so that's the concept, and there's, I don't know, half of them all of mechanical engineers who are working on large eddy simulations and trying to figure out how to do this. Maybe Jim's one of them, I don't know. No, okay, but at least he knows some of them probably. So that's one whole branch, is to try to get rid of the turbulence, and basically that's trying to reduce the density of mesh I need. So trying to get rid of this, reduce the spatial mesh. But the other issue is the time mesh, and the time mesh is even worse, right? Because I said I have 10 to the 8th time points, and I only need 10 to the 4th spatial mesh points in the dimension. So in some ways, if I could do something with the time, that really can buy me a lot. I have 8 orders of magnitude. I'd like to try to reduce to 3 orders of magnitude if I could. That would be really nice. So that idea is to say, well, let's separate the fast time scales from the slow time scales. And in fact, all the fast time scales mostly are all chemistry. Particularly after I change to large eddy simulation, where I get rid of the really small spatial scales, then the time scale of diffusion over this big mesh is kind of slow, and so I can go to a time scale that's completely controlled by chemistry. So we already told you, how do you solve stiff differential equations? Use a stiff solver, right? And there's special methods. They're implicit methods, and they're specialized solvers. And what they do is they allow you to take larger time steps than you would be allowed to use with explicit methods where you'd run into numerical instabilities. If you try to use an explicit method with a big time step, it's much bigger than the real physical time scale. You'll get some crazy oscillation. But if you use the stiff solvers, you can get away with time steps that are much, much larger than the real physical scale. So that allows you to go from 100 picoseconds up to maybe 100 nanoseconds. Get rid of 3 orders of magnitude of time step by using a stiff solver. So that's pretty good. 3 orders of magnitude reduction. We'll go for it. It's not only reducing the CPU time, potentially, but it's even more importantly reducing the number of points you have to save. Because when you run this calculation, what Jacqueline Chen ends up with is a list y at every xn, yn, zl times z, something like this. Alpha, I don't know. That's the output of our program. Okay, so how big is this object? This is 200 times 10 to the 4th times 10 to the 4th times 10 to the 4th times 10 to the 8th. Right, that's how many numbers she's going to get out of her simulation. So actually, her biggest problem is not actually solving the simulation. As long as she can get the 1 month of CPU time, she's good. She's got the solve. Her problem is how to analyze her data. Because now she has this much data that she has to figure out how to say something rational about it. And so she has like a whole army of postdocs whose whole job is trying to invent new data interrogation methods. And also this data set is so large, it cannot be stored on a hard disk. In fact, it cannot be stored on the biggest pharma hard disk. So she has to, as the calculation is running, sending the data to different farms of hard disks around the world and filling them completely up, and then sending to the next one and filling them up. So she has fragments of this data set stored all over the place. And then she has to, if she wants to make a graph, she has to like have a special graph software. It looks inside this data farm, gets some numbers, looks inside this data farm, puts it all together in some way. So that's a pretty hard project. Okay. Now, if I can use a stiff solver, I don't need to use so many time steps. So if I can get this down, say 10 to the 5th, at least I got rid of 3 orders of magnitude of my data. Right. So now I just need one data farm maybe instead of using all the ones that Amazon and Google own or something. Okay. So this is a pretty big advantage to do it this way. Now the disadvantage, as you know, is solving implicit differential equations is way more expensive, right? Because you have to solve an implicit nonlinear algebraic equation at every time step. And in this case, it can be a pretty complicated equation because if I have this many state variables, so 10 to the 4th times 10 to the 4th times 10 to the 4th, so 10 to the 12th times 200, so 10 to the 14th at each time step, that's my current state. And I'm trying to solve a nonlinear algebraic equation in 10 to the 14th unknowns. You need a pretty good solver. I mean, I know backslash is good and fsolve and stuff, but I really don't think it's going to work. So that's a really serious problem. So the next trick is to say, okay, well, I only need the stiffness is only happening because of the chemistry. So I can solve all of the finite volumes separately. So the idea is to split the problem up. I'm going to solve the chemistry using a stiff solver only at one finite volume at a time. And then I'm going to do the transport some other way. So what I'm going to do is I'm going to rewrite this equation as my unknowns dy dt is equal to some kind of transport term and sometimes reactant term. And this term is local. All this in this equation, this is really saying dy at position x depends on this at position x. Whereas to compute these guys, I need to do finite differences or something from adjoining finite volumes. Right? I have to do fluxes from the adjoining volumes. So these guys are sensitive to not just to my local value of y at this finite volume, but also to the neighboring values of y. But if I don't worry about them, if I break it up, I have this local thing and this non-local thing. This one is local, it's stiff. This one is non-local, but it's not so stiff. And often it's linear or nearly linear because the transport terms are mostly linear. And so I have specialized solvers that people have worked on for many years for each of these things. So for the stiff thing, I have things like ODU15S, I have DAEPAC and DASPAC and DASL and sundials and all those programs that people have written, spent a lot of effort to solve this problem. And similarly, there's a whole bunch of people who spent their whole life trying to solve the convection diffusion problems, the non-reacting flow problem. And so I can use specialized solvers that they have. So I want to split this up. And what I really would like to solve is I'd prefer to solve dy dt equals r and dy dt equals t completely separately if I could, because then I can use specialized methods that are the best for each. So now to figure out, well, this is not really the real equation because it has both of them added together. How can I handle that? So this operator splitting recipe is solve dy dt equals to t for a while. And at the end of this process, I'll have y at t final. And then, so I'll solve this equation with y equals y naught. That's the equation system I'm solving, the transport. I do some transport for a while, I get some values of the y. Then I take these guys, and I solve the reaction equation starting from y equals y final. How to write this? Y of t0. Okay? And I solve this one for a while, and I'll get a different, some different y of t final. All right, and the simplest splitting thing says just keep going back and forth. Boom, 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 boom. And in the limit where I make this t final minus t naught to be very small, then maybe I might expect that they might converge to the same solution as the coupled equation. All right, so that's the concept. Now, if you do it this way, it doesn't work very well. You need to make this delta t incredibly small to get any accuracy. However, you can do a slightly more clever version, which is I solve dy dt equals to t starting from y t naught, so y naught, and I solve this to give me y at t plus delta t over 2. Then I solve dy dt is equal to r, starting from y of t naught equal to, call this y star. Y star. And this I integrate out to y of t plus the full delta t. I'll call that y double star. And then I solve this one again. And I solve starting from y of t naught equals to y double star. And I integrate that out for another delta t over 2. And this one I call my y final. And that's the one I use. So I take a half of a transport step, sort of like I'm starting to do the transport, then I suddenly, oh, hold on, I got to do my reaction. Zip, I do my reaction. Then I do the other half of the transport after that. And if you could do the analysis of this, it turns out this thing converges to the true solution of the coupled equations with second order accuracy. So if I make this delta t, if I cut it in half, the precision increases by a factor of 4. If I cut it by a factor of 10, it increases by a factor of 100. So this is looking more promising as a way to do it. This is the most popular way to do it. So this recipe here for operator splitting is called Strang splitting, named after Gil Strang, who's a professor in the applied mathematics department here, former head of SIAM, the international body for applied mathematics, and also author of a fantastically great linear algebra textbook, which maybe some of you guys might have seen some videos of his. So he invented this in 1968. I was 5 years old. He didn't know that his invention was of any practical use, being a mathematician. So he just published that paper. Now, in the meantime, this paper is like a citation classic. It's like cited like, I don't know, 20,000 times. He had no idea. He never looks at citation lists. He's a mathematician. So I was working on this problem, and let's see. Let's back up. So this is how we usually solve it, right? We usually solve the problems of the operator splitting. Sorry, let's be able to see it. And so when we like to solve it this way because I can use specialized solvers. I use a transport solver here. I use the stiff solver here. This one I can parallelize because I can do a different ODE solution at each finite volume. So if I have a big computer, a big parallel computer, say I have 10,000 nodes, I can solve 10,000 finite volumes simultaneously in this step. So the CPU time is reduced a lot. So it parallelizes easily. So this is really popular. This is the main way that people do things. And then in the ideal case, you do it with a certain guess of delta t, then you try delta T divided by 5, and if you get the same result, then you publish it. Okay? And you think, yeah, you've converged your solution. However, what I found doing this is I was trying to find flames. I was trying to calculate the positions of flames. And what I found was that with the delta T's that I would try, sometimes I would get a qualitatively different solution depending on the delta T I chose. And so in particular what I found was that I was solving burner flames. So I have like a burner here, and I should have a flame on top of it like this. And there's two importantly different cases. One is where the flame is floating above the burner, and one is where the flame kind of goes all the way down and touches the metal. And you've probably seen both those cases, like a Bunsen burner or something like that. Sometimes if you get the flow rates high enough, the whole thing will lift off and be floating there. And sometimes if you slow the flow rates down, what they say, the flame will anchor to the metal. Some piece of the flame will actually touch the metal. Usually it's like if you have a lot of times you have a case like this. You have like a metal piece. Here's your mixture coming in. Out here's the air. And a lot of times the flame will come and it'll actually touch this metal piece here. You know, a flame looks sort of like that. Have you ever seen a flame with this? Anyway, this is a common thing, anchored flame. If you just have a slow speed burner, that's what you get. If you go high speed burner, you can make the whole thing lift up and sort of dance around if you look at the flame. All right? I'd probably see the same if you look at a piece of wood burning. If it's burning well, the flame will be lifted off the wood. You'll see a gap between the flame and the wood. If it's not burning that well, you can see the flame, bits of the flame actually touch the pieces of wood. Okay? So that's a very important thing for a combustion guy. So to me, this is a big deal. So when I solved it with one choice of delta T, I get this solution. When I solve with another choice of delta T, I get this solution with a nice big gap. Now, they both can't be right. And so I was a little bit alarmed because it's really different, right? So I thought, I didn't really care that much about the dynamics of my problem. I just wanted to make sure that the steady state flame I ended up with was the right one. So if you're interested in steady state problems, this is a really important thing. You want to make sure that your solution really converges to the true steady state. So what I demonstrated experimentally is this triangle splitting method is not reliable to converge to steady state. Now I believe if I made the delta T tiny enough, probably I would converge to the correct steady state. But I don't know how tiny I have to go. And I can't really judge my convergence criteria very well because at some point of delta T, suddenly it jumps from one solution to another solution that's qualitatively completely different. And so the convergence is not smooth and continuous. It's like it's converging, jumps to something other solution. And I don't know where the jump happens. And I don't know if I keep going further, we'll jump to something else. So this makes me very loath to publish the paper, right? So I don't know. So I was agitated about that. So I started working on trying to fix this splitting. The problem was this string is really smart. So his splitting method is really good. It's stable. It's pretty accurate. It's really hard to beat it, actually. And so I published some papers, and they weren't that good because they really didn't improve it that much. But then I had a really smart postdoc named Ray Speth. Now works in the aeroastro department. And he came up with a different way to look at this. And he said, if I have a problem that's like this, I can always add some constant to this and subtract the same constant from this, and I'm really getting the same problem. And so now the thing is, can I cleverly choose this constant so that, for example, my steady state solution is going to be good? So how to figure out what constants to choose. And so the methods where you add these constants are called balancing methods. So it's trying to balance the operator splitting scheme. And what Ray's method, very simple balancing method. So this is called simple balancing. So I may have a slide that shows it. There we go. Here we go. Simple balancing. You choose the C to be the average of your right-hand side at the previous time step. Okay, now the idea here is as you're getting close to a steady state, the previous time step is not going to be that much different than the current time step. And so this average number is going to stay more or less steady as you get close. And so what you're really doing is adding the sort of the average of these two guys to each of them from the previous step, and that has the consequence of really changing the solution. So let me just show you. So the left-hand side is what strang splitting does. It's the blue steps are the blue steps are the transport, and the green steps are the reaction. And what's happening is I did a half a transport step, then I do a reaction. The reaction sort of jumps me off the trajectory, then brings me back on the trajectory, then overshoots, because I do a whole delta t step of reaction. And then I have to do a half step of transport back. And so I get from the black, one black dot is the first point, and the other black dot is this one I call y final. And that's showing what happens. And it just repeats like that over and over again. And it makes sense. If you're close to steady state, then if I just take one of these terms, without the balancing, take the transport, it's going to head away from steady state, because at steady state, the transport and the reaction are balancing against each other. Typically, you have something transporting in and it's being consumed by the reaction, or something's being created by reaction and it's being transporting away. And they have opposite signs. If I only put one in that has a certain sign, then I'm going to move away from the steady state. And then I need the other one to bring it back. And the reason why strang splitting has trouble is it's trying to do these, it's doing these huge excursions away from the steady state at each time step, with the hope that it ends up back at the steady state. Right? That's the way it's supposed to work out. And to second order, it does. It's because it's pretty clever about how it works. But it does its crazy excursions. Now, if you have a nonlinear model, the further you do excursions from the real trajectory, the bigger the error you get. So if you do the balanced method, you can see what happens is that when you get to steady state, all the steps are just moving you along the steady state trajectory. They're basically maintaining the steady state. And that's because I added, now it's like transport plus half of transport plus R, something like that. And probably there's a minus sign here. Something like that. So I'm getting rid of half of my transport, and I'm adding in half of this. So I've changed. Before I had dy dt is equal to t, but now I have dy dt is equal to a half of t. I feel like I made a sign mistake here. So half of t minus half of r, something like that. And this can't be right. I must have a sign. Maybe this is not half. It's not the average. It's a half. It should be minus. It's like these two should be added. And these guys are canceled out, so basically the OIT is going to be 0, which should be at the steady state. So I'm sorry, that previous slide had the sign wrong. This is what happens as the solution. If you do strang splitting on the left, you get more accuracy as you cut delta t, but it's only it's not getting any better. It doesn't matter if it's near steady state or away from steady state. It treats everything equally. The strang splitting. In the balance splittings, as you get to steady state, all of a sudden the errors drive exponentially. You see this is a logarithm of the error, logarithmic plot. So you get tremendously great convergence to the real steady state once you get anywhere close to the steady state. Now the cost of this is that because the formula, which has a sign mistake, I think, it depends on yn. It makes the whole thing numerically more unstable, because it's like an explicit thing. We're using what happened in previous time to correct our equation for future times. And so you are more likely to numerical instabilities. So then Ray invented an implicit version of that, and also a higher order method, and that's called rebalance splitting. The equation is way too complicated for me to write down, since I can't even write down the minus signs correctly in this one. But you're happy to read the paper. It's in Siam, and he has the equations for that. And if you put the second order one in that's implicit, then the thing is just as stable as strang splitting, but it also has this great property that as you get close to steady state, it exponentially converges to the solution, which is sort of like how Newton's method is really so good. It's sort of like that. You get a lot more decimal places really fast once you get close to steady state. All right, that's enough. Enjoy Thanksgiving. I posted a bunch of readings and things about Metropolis Monte Carlo and stochastic stuff that we're going to talk about next week, and also a little bit more about models versus data. So do the reading when you get a chance. Say hi to your families. Say hi to your friends. Have a nice time.